All right, this question says, define electromotive force, e.m.f, for a battery. So we want to sort of first think about e.m.f is a voltage. So in general, sort of what is voltage? Is the energy per charge. But for a battery, e.m.f is different than PD. So it's converting other forms of energy into electrical energy per charge. Okay, so energy per charge is the key idea with voltage. You can also define e.m.f as the total work done per unit charge as charge flows around the circuit, because the charge is sort of doing work in the resistors, but even if there's internal resistance, like we see in this example down here, so the total work done, even the work that's sort of, lost, not doing useful work, but the total work done. So you kind of look in like the textbook definition for e.m.f might be something like the total work done per unit charge. So work and energy are the same thing. You can kind of think about this lots of different ways. In general, voltage is energy per charge, and e.m.f is a type of voltage. But you really do need to sort of distinguish between this type of voltage and potential difference. The PD, the terminal PD at the battery, the e.m.f sort of here, the potential difference across the resistors, all of those are voltages, right? So we need to kind of distinguish that. And so one energy consideration with e.m.f is that here is where we're converting other forms of energy. In this case, a battery converts chemical energy into electrical energy. And again, per unit charge, right? So that's sort of the energy consideration. I'm going to define it as the total work done per unit charge as charge flows around a circuit. And you don't have to copy my language. You can if you want to. Cite me. Cite the textbook. That sort of agrees with their textbook definition. Put it in your own words as long as you get those key ideas there. So 1 mark for that. Question goes on to read, a battery of e.m.f 6 volts and internal resistance 0.5 ohm is connected in series with 2 resistors X and Y, as shown in figure 6.1. The resistance of X is 4, the resistance of Y is 12. Calculate the current in the circuit. In order to get the current in a circuit, we sort of think about, we have an arrangement of resistors, plus there's internal resistance we need to account for in a series circuit. So based on how much we've resisted the flow of charge, that will determine how much current can be drawn from this battery that has a certain e.m.f, a certain energy per charge, voltage. So the first step to solving this is to really calculate what is the entire circuit resistance, recognizing that there's 1, 2 external resistors, but there's a third sort of resistor in series, right? The charges still have to go through this, kind of consider it like another resistor, even though we know it's, just sort of the resistance in the battery itself. So we'll sum it like R1 plus R, let's call it Rx plus Ry plus lowercase r. That's the symbol we use for internal resistance, right? So that's all the resistance in this circuit. Go ahead and take out a calculator and let me know what is 12 plus 4 plus 1/2. Yeah, that's right. I just did that mentally. Okay, I didn't even use my calculator. Thank you. All right, so the current now, I, for the series circuit, the current's the same everywhere, so there's one answer for this. And since we've already accounted for the fact that there's going to be some lost volts, we're just going to kind of use this voltage, right? In other words, we already know that there's a resistor in here, so we don't have to calculate the terminal PD. In fact, we couldn't because we don't know what the current is yet. So we have to use, we've already sort of accounted for the fact that there's internal resistance by summing that into our circuit resistance. So we've got the 6 volts of e.m.f divided by the 16.5 ohms of resistance. A volt per ohm is an amp. And 6 divided by 16.5, I'll also do mentally, it's 0.36 repeating, of course. And so I'd be tempted to call that just 0.36, because the 363, right, would round down, so we'll just sort of round it to 2 significant digits. 0.36 amps should be the current in that circuit that you calculated. If you didn't get that answer, give yourself feedback right now. So you're like, oh, I didn't add in, I didn't know we had to sort of do that, or you might have got caught up with like the V equals E minus IR, sort of equation. Maybe we'll need that eventually. The terminal PD across the battery now. The terminal PD across the battery is the next thing to calculate. So keep in mind that there is 0.36 amps in this series circuit. And the terminal PD across the battery. What's an equation for that? V equals E minus IR, the one we used for our lab work this week. Terminal PD is this one. e.m.f. they said was 6 volts. Now that we know there's 0.36 amps going through this circuit, it's going to go through the 0.5 ohm resistor, internal resistance of our battery. And so 0.36 repeating, I've got that still in my calculator, so I'm not going to sort of round it down. I'll just keep that times 0.5. That gives me 0.18 repeating volts, right? Those are the lost volts. So I have the terminal PD is equal to the e.m.f 6 volts minus the product of I times lowercase r, which is the lost volts, 0.18 volts. So if I make that negative in my calculator and add it to 6, that's a convenient way to calculate that. And I'm solving for the terminal PD as 5.8, 5.8181 and so on. So that would be this single mark right here. Should have got 5.8 based on this working right here. Make sure that you're indeed showing your working, how you sort of arrived at that solution. The question goes on. Resistor Z is now connected in parallel with resistor Y. In the circuit in D, the new arrangement is shown in figure 6.2. It says resistor Y is made from a wire of length L, diameter D. Resistor Z is made from the same material as Y. The length of the wire for Z is L over 2, and the diameter is D over 2. Calculate the resistance R of the combination of resistors Y and Z. That sounds pretty tricky. So when the questions get tough, we got to sort of have a very careful way to sort of approach this calculation. All right, resistor Y, we know its resistance, and they tell us sort of what it's made out of, L, diameter D. Resistor Z is unknown, right? We don't know its resistance, and so we're going to have to calculate the resistance of Z from this information using the ideas of resistivity. So remind yourself that resistivity is R times the cross-sectional area. So the resistance times the cross-sectional area divided by the length. And so the quantities here are a big clue. It's telling you that this resistor, which we know its resistance R, has a length L and a diameter D, which is related to the area, right? We can assume circular cross-section for wires. So resistor Z, the fact that they say it's made from the same material gives us permission to sort of say, well, they have the same resistivity then, right? The resistivity is sort of like intrinsic to the metal, like how basically it's physical properties, chemical properties. How tightly does it hold on to electrons? And then we have some adjustments to make for Z. So it's half the length and half the diameter. All right, so let's consider how we might calculate what is the resistance of Z based on this, okay? Let's set it up as a ratio. Yours and my favorite. So the ratio of the resistances RY to RZ, let's go ahead and flip that around. Let's make it like the ratio of the resistances RZ to RY. This way RZ is in the numerator. That's kind of the one we want to know, the resistance of Z. So let's put it in the numerator. It's like easier to solve for. Then we're going to use this equation here. So remember that Y just had everything kind of, you know, sort of like a unit length here. So if rho equals RA over L, then R equals rho L over A, this form of it. So this is what R is equal to. It's equal to the resistivity times the length divided by the area. And so for Y, I can just kind of leave all those, you know, letters the same. We'll just call made from the same material with resistivity rho. The length is L. The area A from this diameter D is just capital A. Okay. Now let's see how we have to sort of manipulate those variables according to Z here. Keeping in mind, we can substitute in the value 12 for this denominator. So on this side of it, we've got the resistivity rho, which is the same. We have L over 2 now, right? So I'm going to write it like this. Set up a fraction up here. It's going to be L over 2. Okay, that's the length. And then the area down here, okay, would go in the denominator. But how does the area change if I half the diameter? So if I have a circle and I cut its diameter in half, that's the same thing as cutting its radius in half. So if this radius led to an area A that's equal to pi r squared, then we're taking 1/2 the radius. And so we have 1/2 the radius sort of squared. And so what is 1/2 squared? It's 1/4. By cutting the diameter and therefore the radius in half, we've reduced the area by a factor of 4. Okay, so we've reduced it by a factor of 4, right? And so in other words, when we square 1/2, we have 1/4 sort of in the denominator here, right? Or another way, it's easy to sort of lose track of these complex fractions, right? So keep in mind, we're substituting in here into this denominator, rho L over A. Okay, this 2 came from the L over 2. So A here is going to be 1/4. So it's kind of like we could put 1/4 A, but that's the same thing as going to be like 1/4 A, right? So the 4 goes back up to the numerator. Or you could put like 1/4, you know, put it, you know, fractions within fractions, but it gets kind of tough here. Let's reorganize this to like move this A up to the top and move this 2A down here. So A over B over C over D. We're dividing by a fraction, which means we're multiplying by its reciprocal. We kind of like just multiply the reciprocal of this. That, so we have the numerator now. So RZ over RY. The numerator is 4 rho LA over the denominator here. I've got 2 rho LA, right? There's my rho LA2. There's my 4 rho LA. So that's what it sort of all boils down to. The rhos, the L's, the A's cancel, and I realized that the ratio of these resistances is 4:2 or 2:1. Okay, so now I could say, what is the resistance of Z? If I know the resistance of Y, 12, and I know that their ratio is, you know, 2:1. Multiply both sides by 12, or you can say, oh, well, Z is twice the resistance of this. You could solve it. You can just kind of think about it and go, the resistance of Z must be 24 ohms. If you half its length, right, then you're sort of changing this, you know, so like doubling, it's going to be more resistant if you make its length longer. But if you make the area, you know, sort of also smaller, well, that's also going to have an effect of, you know, less room for the electrons to flow through. So both of those effects end up increasing the resistance. Right? Yeah, I think that's right. All right, so now we need to calculate what is the resistance of this combination. So all we did was calculate sort of Z. Now we've got what's the combination of resistors for a parallel circuit. So it's going to be 1 over RY 1 over RZ. And so 1 over the parallel resistors is equal to 1 over 12 plus 1 over 24. 1 over 12 is the same thing as 2 over 24. So 2 over 24 plus 1 over 24, 3 over 24. And then we take the reciprocal or sort of the inverse of both sides. 24 over 3 is 8. So the combined resistance of these two resistors, and the answer to this part 1 here is 8 ohms. Because we can solve for the parallel resistor. Once we deduce the resistance of Z from this bit of information, we plug it back into our equation for calculating resistors in parallel. That's a very tough question. Lots of steps to it, lots of chances to make mistakes. And so you have to have a very careful way of approaching it. Lots of practice with this one. Help you lead to success. The mark scheme, you want to make sure we're looking at an 8 ohms for that. Complex fractions is tough, you know, you can kind of be confused. It's a state and explain the effect on the terminal PD across the battery. A numerical value is not required. So because we've now connected this new resistor in parallel here, what's that going to do to the terminal PD? What you have to sort of reason through here is to say, if we've added a resistor in parallel to the 12 ohm resistor, we've effectively reduced that sort of part of the circuit. Instead of it being a 12 ohm resistor, now we just sort of calculate what's the combined resistance of that parallel branch. In other words, we've opened up a new path for the electrons to flow through. Great. Internet connection is unstable. Stand by. So if we've opened up more paths for electrons to flow through, or we just kind of think about it like, well, this part right here is now 8, then we have 8 plus 4, 12 and a half. Instead of 16 and a half, we only have 12 and a half ohms of circuit resistance, right? And so that's less than the 16 and a half we had before. So if we're less resistant to the flow of charge, we're going to draw more charge from the battery. The whole circuit is going to draw more charge now. Just like we calculated the current in the first part of this, we could calculate it again and we'd see, okay, if there's more current flowing through the battery, then we're going to lose more volts, right? Because the way that we calculate the lost volts is the current times the internal resistance. So that's not changing, but if the current goes up, we've lost more volts, and therefore the terminal PD is going to go down. Because we're subtracting these lost volts, remember, away from the EMF to calculate the terminal PD. So you have to kind of just think through all of that in your mind and kind of use the equations to help guide your thinking. Let's put all that down into words now. So the effect on the terminal PD is going to be more current is drawn from the battery due to less circuit resistance. Right, because we've opened up a new path, we've reduced the overall circuit resistance, which means we're going to draw more current from the battery. So more lost volts. Means terminal PD will decrease. Right, we'll have less terminal PD because we have to subtract more lost volts away from the EMF. That's how we calculate terminal PD. 2 marks for that. Moving right along, it says, for the circuit in B and C, show that the ratio of the power developed in the external circuit in figure 6.1 compared to the power developed in the external circuit in figure 6.2 is approximately 0.8. Right, and so this was the final one. So we need to calculate the power developed in the external circuit in both figure 6.1 and 6.2. And we should be able to show that the ratio of those powers is 0.8. So the power developed in the external circuit in figure 6.1, what do we know about it? Well, the external circuit is sort of, this. So we're not talking about the internal resistance, right? The external circuit is here. What's the power developed in these two resistors? Well, we could calculate the power developed in this one. We know that the current in this circuit was 0.36 repeating, right? So we could calculate the power as I squared R, because we know R. And so we'll take I squared R for this one, plus the same current I squared, but times this R. And then that would give us the total power developed in the external circuit for figure 6.1. So the calculation becomes 0.36 repeating squared times 4, right? So the 4 ohm resistor, that's I squared R, plus 0.36 repeating squared times 12. For the 12 ohm resistor, I squared RY. 0.36363636 squared times 4. I get 0.5289 watts for that. 0.36 repeating squared times 12. I get 1.586 for that. So the total power developed in the external circuit for figure 6.1, I'm getting 2.12 watts. I will now make a note of on my whiteboard. 2.12 watts, that's my numerator. That's the power I get in the external circuit for my series circuit. Now let's consider this figure and doing a similar calculation where we're going to get what's the power developed in, again, the external circuit, so these resistors here. Now, for this one, we might just want to calculate the total power of the entire thing and maybe subtract away what we're doing in the battery. I can think of probably many paths to the solution here. I'm not sure which one is the most efficient or elegant. But let's consider now that we know there's 6 volts. Remember, we already know that the combined sort of resistance of this is 8 ohms there. If there's 8, 12.5 ohms of total circuit resistance, then we could calculate the current drawn from the battery, V over R, and this might be just sort of overkill for this. I might not need to go this route. 6 over 12.5 means that the current in this situation is 0.48 amps. So we can calculate the power developed in this resistor because all 0.48 amps are going to go through this. Here is where they'll sort of diverge. So we shouldn't use I squared R anymore over here unless we're going to calculate like how much I is going this way, this way. We can do a calculation right here though to say, well, what's the voltage drop across this one? Because if we had 0.48 amps going this way, then some are going to sort of drop across this. 0.48 times a half. So we're going to have 0.24 volts dropping, lost, right? The sort of the voltage drop, the lost volts here. So the terminal PD is going to be 6 minus that. 5.76 volts available to the external circuit. And maybe that's all we need to do to solve it. We could just say, well, if the power in the external circuit is going to be V squared over the total circuit resistance, since we already know that's 12.5, we could just do maybe 5.76 volts squared over 12.5. I think that's maybe a good way to get it. Square that, 5.76, and divide by 12.5. And so we get a total sort of power, again, using the V squared over R equation of 2.65. And remember, the top one was like 2.12. 2.12 divided by 2.65 is indeed 0.8. So unless we serendipitously stumbled upon the correct answer by doing it incorrectly, which is nearly impossible, that's a good way to sort of approach it. My initial thought, sort of with this was, okay, once I know the voltage sort of here, I could calculate how much of this voltage drops across this, and then I know the remaining voltage, and I could use the same V squared over R for these resistors. But again, if all we care about is the total power in the external circuit, we just got to be mindful of, well, there's all of the volts available for the external circuit, since we can, subtract away the lost volts. And then that's the total circuit resistance. Again, by collapsing this down into an 8 ohm resistor, a 12 and a 24 ohm resistor in parallel, make an 8 ohm resistor in series with 4. So there's 12 plus the other half for this one. And so that's where I get the 12.5 ohms of total circuit resistance, very similarly to how we calculated it for figure 6.1 to get the first answer to the current there. So that's how you can show that the ratio of the powers developed in the external circuits for figure 6.1 and 6.2 are 2.12 and 2.65 respectively, where the ratio is 0.8. This has been another worked example with Dr. Schleich. We'll see you next time.